Okay, here is our quick video overview of the gas law properties unit. First thing is our kinetic molecular theory. With a kinetic molecular theory, we need to remember that gases are moving very fast in constant straight lines. They don't change directions unless they hit the contacts or the walls of a container or each other. They don't have attractive forces, and they do not lose energy when they collide. So it's kind of like playing a game of billiards where the balls never stop moving. So gases, when we talk about gases, they're only dependent on four variables. They are volume, temperature, amount, and pressure. You will notice that the substance, the actual type of substance, does not matter here. So it doesn't matter if it's nitrogen gas or methane gas or carbon dioxide gas or oxygen gas. It's only these four variables that determine the physical properties of gases: volume, temperature, amount, and pressure. Okay, let's review volume first. So volume is that space occupied by a substance. Remember, gases fill their containers, so when we measure the volume of a gas, it's the same as the volume of the container itself. Now, we're going to be talking about two different types of containers in our unit here. One is rigid, which means the volume does not change, and the other one is flexible, which means that we can change the volume. So when you see these two terms, that should help you understand if volume is able to be modified or not, okay? Temperature is a review topic for us. Remember, temperature measures moving energy. So the more kinetic energy we have, the faster particles move, okay? And if you slow down particles, they get colder, okay? Remember, we're going to have to work in something called kelvins instead of Celsius for this unit. So our temperature scale will not be in Celsius, we use kelvins. And the reason why we use kelvins is because that scale has a 0 point where it's at absolute zero, meaning that we have a 0 point where there is truly no energy versus a random 0 point that the other scales have. This allows us to have a temperature scale with no negative numbers and no true zero that we ever use in our math, which is needed, okay? Now, here's a quick video on kelvins and absolute zero. We're not going to watch the video in this review, but that was something we did in class. The next thing we want to talk about is amount. This is going to be new to us. So the number of particles in a container is something we need to keep track of for our amount. Now, we can't count individual particles of atoms or molecules. They're just too small. So instead, we group them into these groups we call moles, okay? Moles are kind of like the term dozen, where if I said we had a dozen donuts or a dozen eggs, you would know it means 12. Well, for atoms, because they're so small, we don't just use a dozen. We use a huge number, which is 6.022 times 10 to the 23rd, which is the molecules of a gas. So why this number? Well, this number happens to match the actual mass of the same elements on the periodic table. So if you look at the periodic table and you look at carbon, its mass is 12.011. That then relates back to 1 mole of carbon being 12.11 grams, okay? So that relationship aligns. So that's where the number comes from. For our purposes, we just need to be able to use the mole as our measure of amounts in packages. So we'll never individually count molecules. We'll always count them in sets of moles. Here's a little video on how that number came about and more history. Again, we won't do it in his video, but we did watch it in class. The next thing we want to talk about is pressure. That is also new to us. So pressure is this idea that when we have particles hitting the walls of a container, they create pressure because each little collision adds to that pressure, all right? Now, there are three ways that we can modify pressure. We can add or remove space, we can add or remove the number of gas particles inside of there, or we can speed up or slow down the gas particles, okay? So depending on what we want to have happen, we can modify these or change the amount of volume, the amount of gas particles, or the amount of kinetic energy to make pressure change, because they're all going to change the number of collisions we have, okay? In class, we did that FET animation, and we also use it in one of our activities in class. There are three different uses or labels for pressure. They are atmospheres, kilopascals, and pounds per square inch. When we talk about the different relationships, we're going to cover each one independently. So this is about the pressure and volume relationship, which was also covered in that activity we did in class. So if we hold temperature constant and we increase the pressure on something, the volume will get smaller, and vice versa, okay? So we see here that we're graphing what's considered an inverse relationship, where as the pressure goes up, we see volume going down. So as the x-axis gets bigger, the y-axis gets smaller, okay? This tells us as pressure goes up, volume goes down, or as pressure goes down, volume goes up, okay? Now, they change by the same amount too. So if pressure were to double, notice how we go from 1 to 2, we doubled it. Our volume goes down from 60 to 30, so it got cut in half. So they're inverses of each other and they're proportional to each other. Okay? So if we double the volume of a container, what will happen to the pressure? Well, doubling the volume, the pressure will be cut in half. Okay? If we squeeze a full balloon into a smaller volume, why does it eventually pop? Well, because the pressure goes up. Okay? So if you keep getting smaller and smaller volume, the pressure is going to go up. If you have a 10-liter flexible container at 1 atmosphere, if you compress it to a volume of 5, so we cut it in half, how many atmospheres we have? Well, that would be double. Now we have 2 atmospheres, okay? The pressure-temperature relationship is exact opposite of that, okay? So if we have low pressure and we warm it up to medium pressure, then to high pressure, so notice how it gets cold, warm, hot. It went low, medium, high. So those are a linear relationship with the same idea. So if we actually double the temperature from 5 to 10, we're going to double the pressure for that also, okay? Which tells us that as pressure goes up, temperature also goes up. As pressure goes down, temperature goes down. So they change by the same amounts. Because they're the same amounts, again, we call this proportional. So the same amount means proportionality. Directly means that they're the same. So up and up, down and down. So as one goes up, the other one goes up, which means they're going to be directly related to each other, which is a different, before it was inverse. And because they're the same, that means they're in proportions to each other, okay? So if we triple the temperature in a rigid container, what will happen to the pressure? Well, we triple one, the other one has to triple also. So this would be tripling the pressure. Okay? If your tires are low in pressure on a cold day, why is that? Well, it got colder, so the pressure has to go down also, because as temperature goes down, pressure goes down, okay? If we have a rigid container at 1 atmosphere of pressure and 300 Kelvin, if we increase the temperature to 900 Kelvin, so we went from 300 to 900, so we tripled the temperature, what's going to happen to our pressure? Well, it's going to triple, so that would go to 3 atmospheres. The volume and temperature relationship is similar to that of pressure, okay? If we're really cold, we have low volume. If we warm things up, we have to have a bigger volume to keep the pressure the same, okay? So you notice again, it's a linear relationship that happens as long as we keep pressure the same. So if volume goes up, temperature goes up. If volume goes down, temperature goes down. Again, by the same amount. So again, because it's up and down, that means it's a direct relationship. Because it's the same amount, it's proportional. So we have a directly proportional relationship here. So if we double the temperature of a gas in a flexible container to keep pressure the same, what happens to the volume? So if the temperature doubles, the volume would have to also double to keep the pressure the same, to not let collisions be more. Mylar balloons are the ones that aren't flexible, okay? So if we buy them in February when it's cold outside, you leave them in your car overnight so you don't forget to bring them to school. In the morning, they're partially deflated. Do they have a hole in them? No, they don't have a hole in them. It got cold, so as it got cold, the volume of the gas inside went down, so they partially deflate. As soon as you bring them back inside where it's warm, they'll reinflate. Seems kind of weird, but they'll get back to their normal size. In fact, if you buy Mylar balloons, a good employee will tell you that, so you don't worry about putting them in a cold space. If you have a flexible 10-liter container at 300 Kelvin, if you increase the temperature to 900 Kelvin, what will the volume expand to? This again is assuming constant pressure. So we went from 300 to 900, so we tripled the temperature. So this would have to triple. So 10 times 3 is 30. We'd have 30 liters here. Okay? So what about amounts? You notice how we kept all the amounts the same the entire time. Because in most of those relationships, it's nice to keep the amount the same. So let's talk our way through what happens if we add or remove gas particles to each of our other variables. Okay? So how does pressure change if we add gas? Well, pressure is going to go up, right? You put more gases in, more particles means more collisions, more pressure. Remove it, it's going to be opposite, less, less, and less. How will volume change? Well, adding gas, okay, more particles are going to need more space to not increase collisions, so more volume. Removing gas, less particles, less space, less volume. So these are less, more, and less, and less. Again, direct relationship, direct relationship. So how will temperature change if we keep pressure and volume the same? Here's the tough one. If we add more gas in, we have to cool them down so they don't collide as much, right? It's like if you put more kids in the gym, we have to make them walk versus run so they don't hit each other more often. So with more gas particles, to keep pressure and volume the same, we have to cool it down or decrease the temperature. If we take gas particles out, okay, we'll have to warm that up so we have the same number of collisions and then same amount of volume. So if less particles, we need to warm it to keep the collisions the same, so temperature will increase here. Okay, so this is how amount plays a role into these variables. Now we get to the math. Okay, so all these relationships can be put into equations. Okay, and for these equations, we will be keeping the amount the same. So we have the pressure and volume relationship. Here's our equation. Pressure and temperature relationship. Here's our equation. And volume and temperature relationship. Here's our equation. Okay. The ones in these equations mean the start. The twos mean at the end as we do our math. Okay. So it's always like, what are they at the start and what are they at the end? Start, end, start, end. Okay. Let's do some math with this. So we got to practice it. So first thing we want to do is list what we're given for our information, pick the correct equation, insert the values, rearrange if we have to. These are just simple equations, so we may have to rearrange. And then we're going to use the dumb calculator to solve them. So here's our problem. We have a 300 Kelvin substance in a flexible container at 20 liters. If it's warmed up to 350 Kelvin, what will the volume be? So we're talking about temperature and volumes here. So in that case, we know we have 25 liter container at 300 Kelvin. Pressure does not change here because that's kept constant. We don't know this new volume. We know the new temperature is 350 Kelvin and the pressure is constant. So as a result, with pressure being constant, we're not going to use any equations that involve pressure. We're going to use the volume equation instead to solve this, okay? So our volume equation is as such. We're going to plug our numbers in and we're going to solve for V2, which means I'm going to have to move this 350, rearrange it to solve for V2. So we'll end up getting a volume 2 of 29.2 liters if we change this, okay? Now, here's another sample problem with the answers for us. So here we have gas in a balloon. We have the volume, the pressure, the new pressure. We list out our variables. Temperature was the same here, so we use the pressure volume equation. You see the math that we did, and we got 18.5 liters. Here's another example. In this case, we have volume and temperature, and pressure is held constant, so we cross that out. We use a volume-temperature relationship. We rearranged, and we solved for the volume, and now our volume is 54.9 liters. Another example problem. In this case, our volume was held constant, so we have the pressure-temperature relationship. We rearranged it, and we solve for temperature, and we end up with 1463 kelvins for our temperature. Okay, so those were all problems where we had a change in them. We also can solve for pressure, volume, and temperature when there is not a change, okay? So we can find pressure, volume, and temperature with something if we don't have to go from start to finish. So that is possible. If we combine all our relationships together and add a mathematical constant, we can do that. And we get this equation that pressure times volume equals the number of moles times the constant, which we call R, times T, okay? So using this equation, we are going to want to rearrange it in one of four ways. So we either can find the volume, find the pressure, find the temperature, or find the number of moles. And here's the algebraic rearrangements for you, so to help you plug your numbers in when you're solving for volume, pressure, temperature, or amount, which is our moles. So let's talk about solving for volume, okay? So in this case, we'll use this equation. Here is the problem we have, and we are given everything but volume, so we can insert the moles, the R, the T, the pressure, and we get 37.8. R will always be the same. It will always be 8.314. So this number never changes. It's just different moles, temperatures, and pressures we're going to be talking about, okay? If we solve for pressure, we'll now be using this equation, and we plug our numbers in, keeping R the same, and we get 495.5 kilopascals of pressure. If we solve for temperature, we'll use this form of the equation, and again, plug our numbers in, and we find that our R value stays the same, and we get 320.7 kilopascals of pressure with this information. Finally, solving for amount, or which is our moles, so we're going to use the last version of the equation, again, keeping R the same. We end up with our pressure, volume, R, and temperature, and we get 3.56 moles, okay? So this is a very fast run through from all of our notes, but now that you've seen them all, you can fill in your notes and then ask me questions on anything else you may have. Thank you.